Okay, before going to start the topic 4, let's do a little bit of summary of topic 3. So last time we saw the how we can name the binary compounds including ionic and covalent compounds. We have also seen how to write if we have the prefix like 2, 3, 4, like that. And also we have learned the polyatomic ions and oh, by the way, we learned that if we have the transition metal, that's the multiple valency, and they can give transfer multiple. Yes. Oh, thank you. I think something happened here. Is okay? No, I don't think. Is okay? Do you think it's okay? Now.
Can I ask you a quick question about the slide?
Yes.
I was just curious, how do you know the difference between like a 1, 2, 3, like which Roman numeral to use?
Oh, actually, when they will give you, the name, it will need to write the name. You will see the Roman number 1, 2. Then you will know that is this 1 or 2. But if you need to know from the formula, like here, Fe2O3, correct? Like this one, we don't have it, correct? You need to find it out. You remember we talk about the crisscross?
Yeah.
So then forget about it, right side. Then you will see here for the iron charge. And you will see here for the oxygen charge. So when you will look into, you will see this is 3. So that means this is iron 3 oxide. Similarly, I can write here some more example like FeCl2 and FeCl3. So in that case, this is iron 2 and iron 3. This is the transition. So when you the crisscross, so always look into the prefix of the another ion. Yes. So then.
Sorry. I am understanding that. So
Uh-huh.
for, let's say, the middle example, vanadium,
Yes.
how exactly would you do that one?
Yeah, 4 is here. Here, I think this is little bit of exception. The reason is that I think the vanadium charge is 8. The reason here, you can see sulfur actually 2, 4 or 6. So in that case, sulfur charge should be coming here, but you don't see here. That's because of, that's because the vanadium charge is 8 and 2 nullify by here. So we can make sure here. The vanadium having effective valency of 5. Why the valency of vanadium 5? So then how about the sulfur? Yeah, wait a minute. Thank you for asking this question. Yeah, sulfur atom has 6 electrons, could be 6, but the valency, it gives the valency of 2. So if the vanadium is 4, okay, the oxidation state of vanadium 2, 3, 4, and 5. So the valency of vanadium can be 2, 3, 4, or 5. That's for sure. Now let's come for again the sulfur valency. Yeah, sulfur valency 2. In that case, what we have here, let's go back to our lecture. Sorry. Here, Here we go. So here we have vanadium 1,2,5,3,8 sulfide. So normally, as I said, that this should be the 2, 4, 5, but if they ask you 8, that's why here is a 4, because sulfur charge is 2, that's 2 comes here, and here should be 8. We know we can simplify, like if this is V2S8 according to our learning and rule, correct? So in that case, we can simplify the V28 like S4. So this is how here comes. Another I can say what? Magnesium sulfate. What about the magnesium? Magnesium sulfate. Sulfate 2 charge. Okay. I want to show you another example that makes you more clear why we can simplify. So let's first uh, clean it. How we can clean it? Yeah, we can erase. And we will write another example that will make you simple. But that I was thinking. But normally, sulfur charge sometimes 2, 4 comes. So when, let's write now another one. So I think now you got it why? Because they ask you 8, and this is how we simplify and we comes. And we write another one, the ferrous ferric. Now let's write another one, magnesium sulfate. And as we know that from the periodic table, we can get, okay, so magnesium charge is +2 and sulfate polyatomic ion charge is -2. So normally it should be like that, Mg2SO4 2. But if the same, we can nullify, correct? So simply if we have this type of, we can make it simple. And this is how this one and is okay for this compound. Now you got it?
Yeah.
Yes. Yeah. But I will also show that from the periodic table, we will also can get an idea of the charge. You know that from the column left to right, 1, 2, 3, 4, their valency number is also like that. So today, our valency knowledge that we learned last class will be very useful. But let's continue here. We also see now here, so we know that. Oh, by the way, let's talk about it. See, this is, if we consider, this is the periodic table drawing is here. If you look into, oh, sorry. Let's take this one. Okay. If you look into this way, left to right, correct? And if you look here, 1, 2, and then 3, 4, 5, 6, 7. This is our noble gas. That's a completely filled octet, so we will not talk about it. So normally today we are going to do also the Lewis structure. So normally this 1, 2 most of the time represent, not always, most of the time represents the number of valence electron and also the charge. Okay, so most of the time you can get this help from the periodic table. And also, this column number represent the number of valence electron. How? We are going to talk a little bit of later more. Okay, now we also learned about here the polyatomic ions. We know the polyatomic ions are those cation or anion, at least 2 or more elements together. We know the single cation or single anion, but here only the ammonium ion and another one is called the hydronium ion. Actually, these two, this one and this one, is actually polyatomic cation. I'm not sure why they give this one because this is single cation anyway. So this one and this one is polyatomic cation. And if you look into all others, all are anion. Okay, and you need to be little bit of memorize here. And if you look into non-metal, mostly the non-metal and they form the covalent bond by sharing the electron. So metal and polyatomic ion name we also learn and we know now. What is the formula of barium nitrate? That was some practice. You now know the nitrate is -1 and barium is +2. How I know? I know nitrate from here. Find nitrate. -1, see? And barium, first of all, there are two options. We can see the atomic number and we can immediately draw 2, 8, 18. So we can know the valence electron, or we can also get idea from the column that which column it has. So it has like that, we can find it. Here we go, the silver 1. See, silver 1 sulfite. So sulfite 2 and silver 1 plus 1. So this one we don't need to write here, and these two is come crisscross as a prefix here. Okay, you need to do some practice. If you just Google, you will get lots of practice sheet. I can also give you. So just practice and you will be master on that. You will enjoy the chemistry. Which of the following pair is incorrectly named? Guess this one. Magnesium phosphate, dinitrogen pentoxide, potassium sulfide. You know, students always get tricked SO3, SE4, especially during the exam. Everybody gets stressed. So if you are hurry, you may have a confused and mistake here. This is sulfide, not sulfate. Copper 2 bromide, dinitrogen tetrachloride. So this here is mistake. This is the answer. The name for magnesium phosphate and dinitrogen penta and chromium perchlorate. See, I think chromium perchlorate. Which one? This one? Magnesium phosphate, dinitrogen, chromium perchlorate. But this chromium is 6. See, this chromium is 6. I think so. Yeah, B. So you need practice. So that was all for thing. And you know, the department or the homework website always make the homework that student will spend some time on that. Not tough, but you need to think little for doing the homework. And since you most of the student have little bit of experience, I hope you guys will good. Do practice, practice, practice. If you do more practice, you will find the more fluency to do that. And also sometimes we have some exception, we can catch it. Let's now talk about our topic 4, that introduction to covalent bonding. At least we have learned that ionic bonds are formed between the metal and non-metal, but covalent bond forms between the two non-metals by sharing a pair of electrons. In the case of ionic bond, we have seen that it involves the transfer of electrons, where metal mostly gives or donate or lose the electron and non-metal gain. So metals or who donate electron ultimately become the cation or positive ion, and who gets the electron, take electron or borrow from the metal, they got the negative ion and anion, correct? And today we will be discussing and know how we make the covalent bonding and how we can draw the Lewis structure on the basis of covalent bonding. So we know the covalent bonding history. Here the scientist Lewis in 1916 explained how atoms share their electrons to form the covalent bonding. We already little bit of a learn about the octet. You remember when last time I talked the supplemental electronic configuration, like we all want to be stable in the life. So they also want to be happy. They can be happy if their final shell get 8 electrons. So if somebody have a more than 8, they want to be just live away. Like we have lots of rich people in the United States, like Bill Gates, too much money that she donate all the money in charity. I think 95%. Now Tesla, Elon Musk is doing. So yeah, and so like that, if anybody have a too much, they will give away. Give away. We can also do charity is a good thing. So and if we don't have, we can take this giveaway things. So here is also same. So we know the octet. If the octet or final shell 8 electrons, then they get happy. Now the question that there are some exception like hydrogen, helium. So what then their case? Because hydrogen have only one, correct? So we know the first shell has a maximum 2 electron, 1s2, correct? So this hydrogen can make the bond, only one bond with carbon or any other non-metal. This is called the duet. So when uh, this type of exception element can one, especially hydrogen mainly, so this is called the duet. So Lewis already established the octet and duet rule, and as a result to form the covalent compound. So today we are going to learn details about it. Let's see here. For example, before going to the here, I need to show you something. Okay, okay, let's do this glue first, then I can show you. Here, methane, you can see here, drawing. Yes, it's okay. Here we have, actually this is called methane, CH4. We know the carbon valency electron is 4. How? Because carbon atomic number is 6. So first shell 2 and second shell 4 actually. In case of hydrogen, only 1. So they are not metal, they are non-metal. In that case, if you look into here, carbon want to be octet. If they want to be, you want to make carbon happy. Now hydrogen have only one. Hydrogen will happy if they can make only one bond and duet. Okay, duet. So last time I gave you the two friends banana and bread example. So I will talk now about the electronegativity. So electronegativity is the atom's affinity to attract electron. Okay, any kinds of atoms or elements affinity to attract electron. So in this situation, hydrogen is not happy. In this situation, carbon is not happy. So carbon is looking somebody to make carbon octet and happy. Hydrogen is also looking something to make a duet and become happy, like people make a partner, correct? So um, they also try and they try. So their affinity come close, and they say that okay, let's you have one, let's I want to one, so let's make a bond by sharing. So that time this sharing line happens. Whatever the times the bond you will see like this one. Okay, so this line represents 2 electrons. Okay, this is the important things to learn in this chapter. So this line represents 2 electrons. So 1 electron from carbon and 1 electron from hydrogen. Make sense? Yeah. Similarly, since carbon have a 4 electrons, so similarly, carbon said, okay, my 1 electron make 1 hydrogen, let's more share, and I have 4 hand. I have, this is 3 hand, and this is my last hand. So what happened? Hydrogen is happy to have the duet, carbon is happy to have the octet. So this is actually the behind the scene of the covalent bond forming. You guys got it? And you will got it if you know the valence electron. I think last time we talked about very clearly that how actually the valence electron comes. And we can draw the electronic configuration. The first shell 2, second shell maximum 8, correct? Third shell 18 and fourth shell 32. SPD like that. So Actually, we need mainly the octet and duet, and this is why the scientist Lewis find and established that actually this is behind the scene for making the valency electron. So let's going to move forward. I want to show you something. So I will go back to the blackboard here. Okay. So let's consider this is the periodic table, this side and this side. Okay. Now we just learn. Here we have the hydrogen, like one column. Let's see, this is the 2 column. And here we have some, still we start 3, 4, 5, 6, 7 chlorine bromine, and here we have the noble gas. So what happened actually, the periodic trend is a term. So what happened, the electronegativity, that means the affinity of element to attract the electron, is actually less here, less. If you will go like that, the electronegativity is rising, 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 rising. Got it? So this way to this way, electronegativity of the periodic table elements are rising. Okay? And this way is also rising. Just a minute, I need to show you something else also. You can also see this. Oh, I'm not sure you have there. Okay, yeah. And this way and this way is rising. So that means this way, this side, left side, the elements we have, they have the less electronegativity. That means those elements have the less affinity for the electron compared to go to this way. Like 3 have more affinity than 2 and 1. Like 4 column element have the more affinity to electron than 3 to 1. I hope you got it, correct? Yeah. So this is the one periodic trend in case of electronegativity that will helpful when we will draw the Lewis structure, especially for the complex structure. And another thing, now I'm going to show you the first very famous example, and this is simple example. So let's write here, and then we will go back to our slide also again. Okay. So CH2, this is you can it is recorded. However, you can note it. So let's consider CH2F2. This is a one molecule that form a covalent bond. Now the rule is that first we need to select that which element will be our central atom when we draw the Lewis structure. That means the bond with between the element and how we will show the total electron number as a dot. So now we have to choose that which one will be our central element. First of all, less electronegative element will be our central atom when we will draw Lewis structure. Okay? But now you can, oh, then maybe hydrogen. But hydrogen is exception because hydrogen have only one, hydrogen can make only one bond. So in that case, we cannot consider hydrogen. So then now we have option carbon and fluorine. So fluorine is more electronegative. If you look into the periodic table, fluorine have at the 7th column and carbon have in the 6th column. Got it? So that means carbon is less electronegative than fluorine. That's why our central atom will be carbon. Got it? Now we will draw the bond. Bond means that covalent bond we will form. So how covalent bond is formed? Because the valency electron have, the lone pair electron have carbon, hydrogen, fluorine, they share and they make a bond. So now actually what happened here, like that. Carbon have a 4 hand, correct? 4 valence electron, and hydrogen have 2 here. So let's see the it has a lone pair electron 1, and it has a 1 here. So let's 1 plus 1, 2 electron, and 1 covalent bond CH. Here is another. So this is also another. So here carbon had a 4, but remember each line represents 2 electron. Got it? Why 2 electrons? Because they already make a bond by sharing from one from hydrogen and one from carbon here. So here we have a 2. Similarly, they will do with fluorine, and here we'll go for the fluorine. So now uh, carbon have a valency electron 6, and fluorine have a 7. So now let's find what is going on here. So carbon got octet. How? Because here the 2, here the 2, here the 2, here the 2. Correct? So for 8. Carbon happy. Hydrogen got duet. Hydrogen happy. Now let's consider the fluorine, because fluorine have a 7. So fluorine have like 2, 2, 2. So that's 6, and it has 1, and this one share with here carbon and mate. So now fluorine also have a 8, and fluorine is also happy. So this is how covalent bond form. Not only you already learned 2 things. First of all, how covalent bond form, and second, how to write the Lewis structure. Okay. So now you got it. Any questions? Because if you understand one, you can draw a lot. Okay. This is the simple one. Any questions? Okay. So this is how we have to draw, and how we can know. We can learn, as I know that I teach you already, that how to draw the electronic configuration. In addition, you don't need to be every time do that things. You can. Okay, let's go back. You will have your periodic table. Let's see. They'll have a periodic table. So just to go back and first show you, and then we will come back. Let's look into here. Okay, we have another one that's showing the electronegativity trend. This one. In general, electronegativity increase as you go up and across. So this way, this way, this way. This way less, and this way more. And you will get the valency information from here, like hydrogen 1, beryllium 4, 2, 2 to 4, and boron 3 valency electron. How? I will draw some that will make you more clear. Like beryllium, with this is 1 valence electron, this is 2 valence electron, this is 3 column, this is 4, this is 5, this is 6, this is 7. Now you can say how you make sure. Let's do the make sure here. We can use our electronic configuration drawing knowledge, and we can make it. Like in case of beryllium, atomic number is 4. So that means first shell we have 2, and the second shell we remaining 2. And this is the final outer shell, correct? So outer shell number of electron is called the valence electron. Got it? So that means it matches the column. Huh? Now let's see the boron. Boron atomic number is 5. We are telling that this column is number 3 column, and 3 column also represent the valence electron 3. Okay. So let's draw the boron. So first shell we have a 2, and second shell we have a 3. And this is the last shell because its atomic number is 5. Correct? So that means the valency shell, valency electron of boron is 5. Now got it? How then we talking about carbon 4? Because same carbon atomic number is 6. So when we are drawing first shell maximum 1s, s orbital 2 electron, and then second shell maximum 8, but we don't have 8 because carbon 6. So that's why we have only 4. Now you got it how? So now you guys are mastered that how you need to find the valence electron, how you need to. So you guys also know that how we have to make the covalent bond. Now let's go back to our example. Oh, we are, sorry, we are here. Here we go. Here. So, we talk about the methane and we get back to see the CH2F2, another molecule, how we can draw the covalent and Lewis structure. And this is the called the validate Lewis structure. Yeah, so duet rule, 2 valency electron around hydrogen, and octet rule, valency electron around carbon. So when any molecule have carbon, hydrogen or any other non-metals and they will fulfill the duet rule or octet rule, that times our Lewis structure will be correct or valid. Got it guys? How many valency electrons are there in oxygen, phosphorus, and magnesium atoms respectively? Now you guys can tell. If you have a, okay, let's see here. Go ahead, no problem. So first of all, we have oxygen. So oxygen have valency electron 1, 2, 3. Okay, let's draw. Yeah, I'm repeating that. So if any student had a confusion, there will be. So 1, 2, 3, 4, 5, 6. Here we go. So 6, huh? Second, we have phosphorus. Find the phosphorus. 1, 2, 3, 4, 5. Got it? Finally, we have magnesium. 1, 2. So magnesium here is 2. Now, if we want to draw the magnesium, how to? Because magnesium atomic number is 2. So first shell 2, second shell 8, 8 plus 2, 10, and third shell and final shell is 2. Now got it? So this is how you have to move on. And I think you guys are very clear. So your every topic is going to be understandable because these are the basic chemistry. If you don't understand the valency, how to write formula, how to name, so whole life chemistry will be like fair. But if you know this basic, you will enjoy the chemistry. So let's go back. Oh, we did here. So let's go to the next. What is the Lewis structure for acetic acid? So this CH3 COOH is called the acetic acid, and this COOH is the functional group. We see the many compound like that. Okay. Is it close? Oh, oh no, it touches my knee. Sorry. Yeah. Anyway. So acetic acid. Here we have carbon and hydrogen and oxygen. We know the carbon valency electron 4, oxygen 6, and hydrogen 1. In generally, carbon need 4 more electron to get octet, oxygen need 2 to get octet, and hydrogen need 1 to get duet. So let's see here. We know the hydrogen cannot be the central atom. And about the carbon and hydrogen, let's look into here. So carbon is the less electronegative than oxygen. Got it? Because this way the electronegativity increase. So this one you guys need to remember, then you will never be confused. So that means carbon will be our central atom. In that case, we have 2 carbon, correct? So first we will write like that. Then we have here to 1 carbon, we have 3 hydrogen. So they will share the electron with these 3 hands. So first do from the left side. Then carbon also got the one hand. So here is the 2 electron, here is the 2, here is the 2, here is the 2. So each line represents 2 electrons. So this carbon is already happy. Now let's see the oxygen. So here you can see the oxygen is one bond and 2 electron, and here we can do the another hydrogen. Now the question that oxygen here we had the one hydrogen. So what oxygen did here, oxygen say, okay, I will make a pair share of bond with one carbon and one hydrogen. But how about this oxygen now? We have remaining one, because if the hydrogen make the duet with oxygen, now you look into hydrogen is happy and this oxygen is also happy because it has the now 2 to 4 electron. Here is the 2 and here is the 2. So this is also happy. So now the unhappy is another this oxygen and this carbon. So then first let's see the make one oxygen. Here the 2 electron, but still it has the less another and carbon has the less another. So then both are finding the way, the how we can do it more. In that case, it doesn't matter the which way they have the lone pair, whatever the way we have, we will share because we have to be happy. So in that case, our solution, when you will see this type of condition, we can make double or triple bond at the same place. So we can make another one. So now here if we look into 2 plus 2, 4. So if we have 2 plus 2, 4 and we already have a 4 here, so 8 oxygen happy. If we look into here 2 plus 2, 4 and here we have the 4 because each line represents 2 electrons when they make a bond. So now everyone is happy and this is how we need to draw. Beginning you can see that little complicated, but actually no. When you will start to practice, you will automatically find this type of way because you know the carbon for how many valence electron you have. So let's move on. Let's see here. So if we now look into the summary, so what we have then hydrogen satisfy the duet rule, carbon satisfy the octet rule. Even in that case, let's go back here, oxygen satisfy the octet rule. So this is possible. When you have the another hydrogen atom, you don't need to make here double bond. But if you don't have, however, this is a compound, and when any compound formed by two or more non-metals, they always need to be satisfied. Remember, the two or more non-metals, it doesn't matter, but ultimately, if they are covalent compound, that means they have to be satisfied either the duet rule or the octet rule. So when you guys will do, you guys will be very clear to make it. Yes.
If we were asked to draw the rule structure, do we have to draw the duet and the octet rules? You see how like you circle it? Is that
I mean, no, this is no, this is just for us to clear, make it clear. Yeah. Yeah. No. So now you could see they write the total valency electron 24. They maintain here total the hydrogen, carbon, oxygen total they got it. Now let's see the another example. Bromine cyanide or bromocyanide. In that case, 16 valency electrons and 8 lines. So if we go back to our periodic table, I'm going back every time so that you guys already memorize that how you have to do it. So boron, find the B is here, correct? No, boron or bromine? Which one? Bromine, yeah, bromine is here. Here we go. So that means the valency electron should be 7. carbon should be 6. 7 plus 6, 13, and nitrogen 5. Now got it? So here total 16. How? Because boron is 7 plus carbon is 4. 7 plus 4 equal to 11. Wait. Boron is 7, correct? Carbon is 4. 7 for 11, yes. Nitrogen is 5. So 11 plus 5 equal to 16. Yeah. And here you can see the bromine is 7. So that means bromine need only one electron. I mean only one bond, one line. So that means bromine 7. So bromine need just only one more electron. So that means if bromine make just one bond with carbon, then bromine is happy. Now come the carbon is still need to make 3 more bond, correct? Because 3 plus 3 is 6 and these 2 will be 8. And nitrogen, if you see 5, that means nitrogen here have 2, and if 3 electrons can make 3 bond with the another 3, then it will be 6 plus 2, 8. That's why here is a 3 bond with the carbon and is possible. It's scientifically okay. So this is how we make this covalent bond. Plus you also need to write the Lewis. You can see the line. So maybe some books or some video you will see the line, or some you will see the Lewis structure as a dot. This dot represents 2 electrons, and this line also represents 2 electrons. But normally if you look into books or everywhere, you will mostly see the dot. Okay, so Lewis, even some books, some lecture, you will see the Lewis dot structure. So this is up to you. I will prefer the dot. It's better to write dot, but line is also fine. This is also from the the Jumadel book reference, so it's okay. So we saw a couple of examples, and now we will talk about, from the example we have already learned that how we can how the covalent bond form, and there are a couple of conditions that if the covalent bond form and make a covalent molecules, we must have to be satisfy either octet rule or the duet rule. It doesn't matter that how many non-metal molecules we have in the compound. So these two things we learn, and additionally one important things we learn, that we have to first find the central atom, correct? And central atom must have to be less electronegativity, but exception hydrogen. Since hydrogen have only one, we cannot consider hydrogen as a central atom. So these couple of things we learn, and I hope you all are very clear. Now, whatever we have learned, on the basis of the learning, we have some general rules that will guide you. Hydrogen always forms one bond, zero lone pairs. Need to share one electron to achieve a duet. We already got it. Oxygen usually form two bond, two lone pairs, need to share two electrons to achieve octet. Nitrogen usually forms three bond, one lone pair, needs to share three bonds, that means three electrons. One bond, one electron. Got it? Two bonds, two electrons. Because if you want to share two bonds, that means you need two more electrons from other atom. So this is the general rule, that nitrogen three bond, three bonds means three, just we saw the three bond, single, double and triple. Carbon always form four bond, that means carbon needs to share four electrons to achieve octet. And this is our basic rules for Lewis structure plus forming the or making the covalent bond. Now, which of the Lewis structure is a valid representation for COCl2? molecules. Let's count it. Here if we see COCl2, carbon here seems 2, 4, 6, 8. But how about the oxygen? Oxygen seems 2, 2, 4, 6, 8. How about the carbon here? Here is a 4, here is a 6, here is a 8. Now this is not the correct one, correct? This is the, violation of octet rule. Now, if we look into here also, if you count here, too many total electrons. So here is also too many, like the way we find here. So the correct one, if you count, you will find this one. And the total valence electron, 4 plus 6 plus 14 equal to 24. Now you can ask that why 14? 2 chlorine atom. For 1 chlorine atom, 7. Then for the 2 chlorine atom, 14. Oxygen 6 and carbon 4. Yes?
Can you explain the octet rule, please?
Huh?
Can you explain the octet rule, please?
Yes. So octet rules means that every element, when we draw the electronic configuration, we know that electrons are always moving around the nucleus at different energy levels. And on the basis of energy level, we have isolated and got some shell, like, and we represent as an orbital, like S orbital, P orbital, D orbital, that we little bit of discussed earlier in the last class. So our rule is that first orbital can have maximum 2 electrons, S orbital. P orbitals can have maximum 8 electrons. D orbital or third shell can have maximum 18. So this is just number of electrons. So now if we look back into our periodic table, we have the atomic number. Atomic number means the proton number. And in most cases, same number of proton number and same number of electron represents. So that means if we have a proton number, for example, carbon have a 6, that means we have electron also 6. So now, if we can want to draw the electronic movement or how to say, moving around the nucleus, so first shell we have maximum 2. So first shell 2 got 2 electrons. Second shell we have then 4. But our octet rule represents that if the elements need to be stable, happy, they have to be maximum 8. I mean, this is scientists already did the experiment and found it. Okay? So in case of carbon, since we are today talking about the covalent bond, so let's talk this way. The carbon have a 4 electron in the outer or second shell. So whatever the number of electrons in the second shell or outer shell is called valence electrons. Got it? So carbon have a 4. Now carbon is not an ionic compound, ionic element. If it is ionic like sodium, calcium, potassium, they have a tendency to ionize by transferring the electron. But in case of non-metal, they don't have this feature. But non-metal, for example, and carbon can share the electron and make a bond. So that means that you are like you and behind you guys two are friends. So now you guys want to buy a pair of shoe. You guys like it. Let's, for example, the shoe is very expensive. Let's say the $500. But you have a 250 and she has a 50. If your shoe pair leg size is same, you guys can just think that let's share our money together. We will buy this shoe and we will organize and schedule that how we will wear the shoe. Got it, guys? So same thing happens is here. This is funny, but this is how it works. So carbon have a 4 electrons. So carbon look for some other non-metals that who have a similar situation and can share the electron and make a bond and become the octet. Now got it? Yes. interesting, correct? Yeah. Now, we guys can also calculate, like this is a Lewis game or playing game, like little bit of one equation. By applying this equation, we can easily find out the how many electrons shared in bonds, how many electrons, total electron in the octet, and the total valency electron. So if we look into here now, we can see the S equal to N minus A. S means electrons shared in bond. So line. So X have one electron, Y have one electron. So 1 plus 1 share, now got the 2 here, and now Y got the 2 here. And they make this covalent bond. And as I said, all the bond formation is dependent on the affinity of elements to attract the electron. So the minimum affinity or energy need for this element to share or bond. Like I'm walking to you, you are walking to me. If both work, then we can come. But if I only walk to you, so I need more energy, correct? But if both people work and we see that come together, so I will apply some energy, X, Y will apply, and then. So similarly, next we are going to talk that at least we need minimum energy for making this bond, and that's the electronegativity we said. So now this S is the electron share in a bond. N, total electrons for octet or duet rule. So this is the N is the total number of electrons either for octet or duet rule. And here the total valency electron. Valency electrons mean the outer shell of any element, the number of electrons. It can outer shell doesn't represent. It can be the first shell, it can be the second shell, it can be the third shell, and so on. It depends on the element. Like in case of hydrogen, only one, correct? So hydrogen valence electron is one. For some elements, the second shell is finished, especially the lower atomic number. But if you go to the higher atomic number, maybe you need to draw the more shell or more circle. But ultimately, the outer shell, that means the higher the number of electron is finished, there we have to count it. So let's, for example, here apply the cyanide. CN, this is cyanide molecule, but you can see this is -1 charge. That means the cyanide already take 1 electron from others. So now see the N. N represents total electrons for octet and duet. So how many atoms we have? We have 2 atoms. So for 2 atoms, if the carbon and nitrogen want to be octet, octet means 8, correct? So for the 2 atom, the total electron will be 16. Now A representing valence electron. So how what is the valence electron for the carbon? 4, correct? Plus the valence electron for nitrogen is 5. But you see nitrogen already borrow 1. Huh? So we have to add this one also. So then total 5 plus 4 plus 1 is a 10. So now if we subtract the octet electron number minus the valence electron number, then we will got the electron shared in the bonds. So that means 16 minus 10, this 6 electron will be shared and 3 pair of electron. That means 3 bond. So this is how the 3 bond, you know, the cyanide with the carbon like that. So this is how we can calculate. So even if you are confused, you don't know that what to do, how many electrons will be shared and making bond or participate in bond making, you can just follow these rules according to the formula or molecule you are given. you can easily sort it out. See here. So here with the 3 to 6, we have the here 2 electron, we have here 2, and also here 3 to 6 7, sorry, 3 to 6, and here we have 8, but here the minus 1, and then comes 8. So there should be 5 lines in total, satisfy the octet rule with the remaining electrons. So 10 electrons, 5 lines. Here the another example. Carbon dioxide. Yes. So same, now you can do the, you know how to draw it, but if we are asked you to follow this rule, so you have to follow this rule. So first rule, S equal to N minus A. N equal to total number of octet. How many you have? You have carbon 1 and oxygen 2. That means total number of atom or element here, total 3. So 3, 8, 24. Now, how many valency electron? That means A we have. For carbon, we know 4. For each oxygen, 6. So we have 2 oxygen, 6 plus 6. 12 plus 4, 16. That means 8 line total. Now then, find out if we ask that how many, then the electron that shared the bond. So then this is the S. So if we subtract the 24 minus 16, then you will got the 8 shared electron. So 4 pair of bond electrons. So here, this is sometimes the central atom. Obviously carbon, because carbon is less electronegative than oxygen. I think so. Yeah. Oxygen is 8 and carbon is 6. Yes. And then you will have like that. So then here we have 4, here we have 4, and here we have 4 also, like that. So 2, 2, 4, and each line represents 2, so 4. So this is how it will work. See, they write. So you can write the line represent or dot, both are fine. Since your book telling line, you can keep on line, don't worry about it. Carbon dioxide, what we did before, also did carbon dioxide. Okay, then what's new here? Yeah. I think this is just double atoms. We will talk about resonance here. So how many lone pair of electrons does the nitrogen in ammonia have? So you need to find the ammonia structure. Actually, this is NH3, ammonia. And if ammonium, then 4. So how many lone pair of electrons does the nitrogen in ammonia have? So let's draw it, how many nitrogen we have. So yeah, so let's go back to here for the explanation. So they make the bond and they find 1 lone pair here. So 3 single bond and 1 lone pair. So 3 each represent 2. So 3 to 6 plus these 2, 8. So this is how you have to find out. Now we will talk. Okay. I hope you all got it about the covalent bond and Lewis structure. Yeah. Now, as we said, that we will talk a little bit of bond breaking, bond formation, bond energy, and bond breaking. Before that, I want to just talk a little bit of regular. Anything you want to break, you have to do some force. Correct? That's why when we do the bond breaking, this is a kind of reaction called the endothermic. There are two types of reaction, endothermic and exothermic. Endothermic means when you need to apply the external heat or force. And exothermic reactions, that means when the new molecules will form, they will make the new bond, the new molecule will form, they will release some energy. For example, now summer is coming and very soon the 4th July will come and we will enjoy the fireworks. Fireworks is a kind of example of exothermic reaction on human. So that means when the energy will come, which can be as a heat, it can be as a light, like we use the gas to run the motor vehicle. In that case, gas also giving some energy to run the motor vehicle. So those are the exothermic reaction. So first, before going to the bond energy, we should be very clear about that. If we now look into this reaction, if we look into the reaction here, the methane plus oxygen, so we know that carbon dioxide and water molecule will form. But this is not all. Before making carbon dioxide and water, first we need to break the bond of methane and oxygen. Like here, we already learned that this methane bonded with the carbon, correct? This oxygen also bonded like that, correct? So we have to first break this bond, and then when this bond will be broken, then they will try to find the new bond to become satisfied or happy and octet, correct? So this is called the bond breaking and bond making. So actually bond breaking involves the endothermic reaction. That means we need to apply some force or energy, and the bond formation or new bond making or new molecule, it mostly involves the uh, energy release or called the exothermic reactions. So if you look into the ball, stick ball, these are the hydrogen, these are the carbon, and these are the oxygen. So first they will be broken and then they will make the new bond like water molecule. So oxygen like that, hydrogen, hydrogen. So here we have duet and 2 to 4, and then we have here like that. So carbon dioxide we already check it out, correct? So we need here, yeah, we need, I think, 2 to 4. Yeah, so we will see it this way. Yeah, so we need the double bond here. Then the 2 to 4, and we have here. So 2 to 4, we have other. Yeah, like that. So let's move on. Yeah. So now we need to know about the bond length and bond energy. So actually, the distance between, what is the bond length? We are not talking about the ionic bond. We are talking about the covalent bond, correct? Where we are talking that electron sharing is going on. And we also know the electronegativity, that the affinity of element to attract the electron. So what happened actually here, what we mean the bond length, this is actually the distance this bond length is the distance between the electron and the nuclei of the, so the, carbon. So we know that if we draw this, is we have a nucleus, one carbon, and here we have the nucleus, another carbon. So this is the distance between the nuclei of the two atoms. Okay, so this is the distance between the nuclei of the two atoms. This is called the bond length. And bond, as we have already seen, the bond can be the single bond, double bond, and triple bond. Now the question that why the single bond length is long, and you can see the bond length 154, 134, 120. That means that number of bond increasing, bond length is decreasing. And another things you can notice here, the longer bond is the energy is less. When the bond is shorter and increasing the number of bond, the energy is increasing. And this is actually the reason, the attractive force between the electron, and why this is happening, and the reason actually the attractive force between the electron of element and their nuclei. Nuclei means the positive nucleus, because here no electron transferring is going on. So here we can draw like that. Let's, is this the delete button? Yes. So let's draw here like that. So carbon, let's see that the here the electron, and here is the, I'm not so good at drawing, so bear with me. So this is the one carbon nuclei. This is the another carbon nuclei, and this is the electron. So the affinity of electron towards the nucleus of the two or more element actually determine the length and energy. So by these two affinity or two method, we find that the single bond is more length is high, and the number of bond increasing. That means their affinity also changing. As a result, they coming together, their affinity, they coming close together, and their energy is enhancing, and their length is also decreasing. And this is the fashion of the bond length in case of single, double, and triple. So you guys need to remember the single bond is length is bigger than the double, and double bond's length is bigger than the triple. But in case of energy, flip, vice versa. So triple bonds energy is, yes.
What do you mean by affinity of the atom?
So the affinity of the electron, like the attraction of the electron, because we always know the opposite things attract, correct? But here we don't have any opposite pole like positive and negative, because this is not the ionic form. So here the affinity based on the electron of the same elements and their nucleus. So this affinity we are talking here. So as a result, we saw that in case of length, increasing the number of bond, length is shortening, and the energy is enhancing the flipwise. And also, if we look into the thing here, there are some we have little bit of difference. So we need to check out. When we will check out, we will see that this is the regular fashion, and this is the carbon-carbon regular fashion, and this is the carbon-oxygen, this is the carbon-oxygen single, double. This is the carbon-nitrogen single, carbon-nitrogen double, and carbon-nitrogen triple. But actually the length and their energy is vice versa. Okay, this is you have to remember. And also one more things you have to be know, that here we go. Longest bonds are weakest and the shortest bonds are strong mainly because it takes more energy to break the shorter bond because that's a shorter bonds are either two or either third, right? Second or third. It takes more energy and that's why. So that's about your bond length and energy. Now actually we have mostly the practice problem and we will also little bit of talk about the polar and non-polar compound. Yes. Let's see. Compare the carbon-carbon bond in the molecules CH3, CH3 and CH2, CH2. Here I want to help you little bit. I know you know. This is the CH3. You know carbon have a 4 hand. But when the CH2, CH2, you need like that. So from the knowledge of single bonding and double bonding that we learn in the previous, here we go, you can determine that which one is weaker and which one is stronger, correct? So now let's see, here we go. Compare the CC bond in the molecules and then we know the CH3 has shorter and stronger? No. CH2 has a shorter and stronger. Yes, I think this one. Because double bond is short than the single bond but they are more stronger. See here? Longest bond weakest and shortest bond strongest. And even if we look into there now, so see, their bond length and energy. So more energy, more strong, okay? They are flipwise. So you have to find out like that. So CH2 has a shorter because it has a double bond and is stronger than the CH3. See, they draw like that also. Okay. Now, all bonding is based on the electrostatic interaction. As I said, he just asked me the negative charged electrons of one atom and the positive charged nucleus of the other. So if we had the ionic compound, so someone giving, someone taking, and their magnetic charge is nullifying, and they are doing the short straightforward way. But here we go for the covalent. So it depends on the electrostatic interaction, the affinity of electron to attract other, and we compare with the nucleus of the others. So in that case, we will see the hydrogen is a polar or non-polar. So now that see the opposite charge is polar and the equal charge is non-polar. So what does it mean, the opposite charge or equal charge? So now this is hydrogen molecule. You know the term polar and non-polar. Polar means who have an affinity for the water, correct? And the vice versa is non-polar. So now is this the hydrogen molecule? So if these two element or atom have the equal charge affinity to each other, then that will be non-polar. That means the affinity of these two atoms to attract the electron is same. Got it? They both are same atom and their affinity, their charge is equal to same. So that's why they are non-polar. But if we consider some other example, like here, I will come back here again. Like here, hydrogen and fluorine. Which one is more electronegative? Fluorine? So that means fluorine have a more affinity and energy than the hydrogen. So in that case, this compound will be the polar compound. So how? Because if you have the more affinity, they create the dipole moment. Now consider the what is the dipole moment? Dipole moment is the distance between the two charges. Okay, this is the distance between the two charges. So if the distance, the rule is that if the distance between the two charges is higher, that means their polarity is also high. That's why if you, when you will see the two element or compound, I mean element in a molecule compound, especially the covalent, if they are in the equal charge like we saw here, the hydrogen, then this is non-polar. But when you will see that like electronegative elements include here and they are more electronegative compared to other, that means they have more electrons in their side, so they can attract more electrons. So when they can attract more electrons, they have a tendency to become more polar and dissolve in a polar solvent. So this is how actually we look into here. And the dipole moment is the distance between the two polar charges. And this is, we donate as a D. So like here, the fluorine dipole moment is 1.91. So if the distance is any type of this type of molecule, you need to check into the distance. If this distance is so high, that means their polarity is also high. So then very simple things that you need to be yeah. So very simple things that you have to be find the their charge or interaction or affinity. So the simple things to find that, if when you will see the similar type of, that means they are the same. But when you will see the like this type of one is more electronegative, so more electronegative, their polarity is more high because their affinity to electron is more, and as a result their dipole moment or distance between the two opposite charge electron is higher. So that's why. Now the electronegativity, we already talked about the electronegativity. So see, electrostatic attraction are based on electronegativity, the ability of an atom to attract electron. So that's, we already talked this way to this way. And this is also called the periodic trend. It's PT, that means periodic trend. Electronegativity and the polar bond. See, fluorine is more electronegative than hydrogen. So as I say, the more electronegativity, more polarity. So when hydrogen and fluorine bind, the fluorine atom will attract electrons more strongly than the hydrogen will. So this is actually the theory behind the polarity. Let's generalize what we know. The larger the electronegativity difference between two atoms, the more polar the bond. Got it? That we are going to talk. Arrange the, yeah, this is the very exam materials. I want to little bit of explain this. Now you have actually all the question material solution. Normally I supposed to make question from here, but I'm not sure, I don't remember that I keep all the question answer Oh, yeah, I think I keep it because this is I download from the, yeah, I keep it. But I keep all the question solutions so that you guys can practice and it can be helpful for homework because I have lots of question polls so I can make also. So no worry about it. So actually this is the question poll, instructor make question from here, but I have lots of questions. So if we practice these some questions, it will be helpful for you. Arrange the following bonds in order of increasing polarity using the periodic trend in electronegativity. It's very simple. Now you guys know that this way the electronegativity getting higher, correct? So you guys can make that all like don't consider the noble gas. Okay, noble gas means they are already filled their valency shell. We will not talk about the noble. So if we consider here, so obviously it will be more electronegative fluorine, oxygen, nitrogen, carbon, bromine, then like that. So let's see our then answer here. See, fluorine, carbon, then chlorine, carbon. Oh, by the way, I need to also tell this one. So like this way less, least, and this way high. Similarly, this way high, okay, electronegative. This way high and this way less. Also, please keep in this in the mind. So if you can also see it, because let's delete the notation. Yeah. See, the fluorine carbon is most increase of increasing electronegativity, then chlorine, then bromine, then iodine. They skip here bromine, but still after bromine is iodine. So that's why it's okay. Fluorine, chlorine, bromine, iodine, and then carbon, carbon. So you have to be just clear about that. This way and this way. So from the column left to right and from the row down to, sorry, bottom to up, or up to bottom in increase to decrease. Here we have some example: water, ammonia, and carbon dioxide. So here they are partial, positive charge and distance. As we say, we have to just measure the distance. See here. Each CO, sorry. Yeah, so about this distance, we will find the which one is more polar, which one is less polar. Obviously here, the nitrogen is more electronegative than hydrogen, and this is obviously polar. Here, if we consider the carbon O bond is polar covalent bond, the resulting carbon dioxide molecule is a non-polar molecule. See, here is the things we need to be see. That though the carbon is electronegative than oxygen, but when they make the double bond, somehow their affinity and distance is not enough to have the polar. So that's why this is non-polar. So you will see some example more here. Consider the Lewis structure for ozone. Ozone O3, okay? This is called ozone. This is not the oxygen molecule. This is one of the ozone that, you know, environmental people consider if our air have too much ozone, that's not good for us. Consider the Lewis structure for ozone proposed by a student in general chemistry. Which of the following statement about the structure is incorrect? So here if we look, 2, 2, 4, 6, 8. 4, 4, 8, 4, 4, 8. Okay. There are a total of 6 lone pairs in the Lewis structure shown. Total 6 lone pairs? 3, 4, 5, 6.
The central oxygen atom has 2 lone pairs. Yes. There is one single bond and one double bond in the Lewis structure would predict that ozone has 2 different bond lengths. Maybe the double bond in ozone would be harder to break than the single, obviously. So let's see which one is the, yeah, this one, 2 lone pair. Yeah, because there is a one.
So actually, that's all, and you guys have to be practiced. So let's do some practice. So consider the Lewis structure F2CO. Carbon is the central atom in this structure. Which of the following statement about the Lewis structure is incorrect? So if you draw the structure, that will be easy, like here. So this is our F2CO. So let's see here, 4, 4, 8, 2, 4, 6, 8, 2, 4, 6, 8. Okay, so total 2, 5, 6 to 8. Yeah, 8 lone pair is here. Okay, so guys, practice those questions. Use the electronegativity table to see that I was telling that if a periodic table can help a lot for this course. So you have to learn that how to use as much as periodic table you can. So you guys can practice here. Yeah. So actually that's all for today. We don't have, yes, question.
For the electronegativity, you see how like hydrogen is in the top left corner? So let's say if we're comparing hydrogen and neon, which would be more electronegative?
Which one? Let's go back to. Okay, here we have the hydrogen. Corner. This is the increasing bond polarity. So you asking about the electronegativity?
Yeah.
Okay, so let's go back to any of the table. See here. Yes. So here we have the, yeah, so here we have the hydrogen, huh? So what your question?
Like let's say for example neon or
no, we cannot talk about here because they are the noble gas. They are already filled. Okay. They don't do that. But other than that, we can talk.
How about let's say for iron, which would be more electronegative in that case?
Iron?
Oh no, not iron. I'm sorry, not or oxygen. Either.
Yeah. So here, if we consider this way, so this is the most highest. This way, then oxygen, then nitrogen, then carbon, then boron, then it will come. But if we consider this way, then fluorine is the most highest, then chlorine is less than fluorine, bromium is less than, bromine is less than chlorine. So then we can also have to be think like that.
Okay, I see.
Now got it?
So let's say oxygen or fluorine.
Yeah, so oxygen is less than the fluorine.
Yes.
Yes.
But oxygen is more electronegative than hydrogen.
Yes.
And hydrogen would be
less electronegative.
And let's say like for chlorine.
Yeah, this is chlorine.
Hydrogen would be more electronegative in that case, right?
No. Hydrogen is, this side is always less.
Okay.
So
this left to right.
Yeah, left to right. Okay. So this side is like left and right. So here hydrogen is always left. And in this corner, we will not consider the noble gas. So the fluorine 7th column will be the here. 7, 6, 5, 4, 3 like that. Okay. So actually that's all. We don't have to do anymore. Some question, please practice because you also have a solution here. So don't worry. And yeah, see, we have also some practice here.
Some practice of formula. Yes.
You've been uploading the supplements, like the notes.
It depends. Which chapter we need, I will. Like so last chapter I did.
You didn't. For chapter lecture 3, it wasn't uploaded, and then because no. For 1 and 2 it was, but for 3 it was.
Oh no, as I said, that every chapter you don't need.
Okay.
When you need, I will. Like okay. The electronic configuration that I did. You remember electronic configuration supplement for the topic 2 I wrote, but it is still helpful for this chapter.
Okay.
So when you need, I will give. I mean, every chapter maybe you don't need. Like here is enough details, and you already have that nice knowledge about the configuration, so you are fine. And lots of examples. But when I will see that you need something extra, I will definitely give it.
And here we have some practice. Please do that. I think that's enough for your lecture exam. By the way, end of this week, I will be detailing your first lecture exam procedure. Okay? Yeah. So that's all. Today, I want to tell something. Okay, first just